Hello everyone, welcome to the 10th week of interaction session on control systems. My name is Soumya and I am a PMRF fellow at IIT Gandhinagar. So in the last class, what we basically saw was how Bode plots are useful in getting the stability analysis. And there were some very basic or preliminary questions on how Bode plots are drawn, how do we draw the magnitude plot, how do we draw the phase plots, and such things were there. So, in this class, uh, we are going to have some good questions, I would say, for Bode plots. And then we'll also move to the next part, which is based on Nyquist stability criteria. So essentially, today we'll not be covering Nyquist stability criteria, but we'll be seeing that how Nyquist plots are drawn. In the next class, we'll have a few questions on Nyquist stability criteria. As far as the Bode plots are concerned, I would like to go through the lecture that we covered last time and just to give a glimpse of what had happened. So I would not go through the questions, but I would definitely show you something which would be helpful today in case you have missed. And I really hope that you have gone through the lectures. And even if you haven't, I think we can do okay. So we actually had seen that uh, these Bode plots are really good tool to measure the stability of a system. And we have magnitude plot and phase plot, where the magnitude of the closed loop transfer function is varied with respect to omega, and the angles are varied with omega. Today we'll see another method called Nyquist plot. Okay, and in this it would be the real part of the transfer function versus imaginary part of this transfer function in PS plane. So it's not going to be S plane anymore. It's PS plane here. So this is important thing. And then we'll be constructing. And you'll see that most of the times it is going to be semicircle in our cases. But let's see. Okay. So for the plot, we had seen that if it is for a constant magnitude, we are going to have the gain as 20 log magnitude of the transfer function, because we want to do everything in dB scale. Moreover, we also saw what are the benefits of using logarithmic scale. Like uh, you could have larger range of omega. You can have low frequency region expansion. So both of these things are essential when you want to find out some performance parameters, either in frequency domain or in time domain. All right. Then we saw that we will also have phase plots. Then these building blocks were the most essential things. Uh, so having the plots for all of them was really what we saw. So for constant magnitude, it used to be a constant line. When we talk for a term that is more close to integration, like in this case, it is 1 by s. So for 1 by s, we saw that the line is always decaying, or the slope of the line is minus 20 dB per decade. Whereas for gs is equal to s, it is always rising at a slope of 20 dB per decade. All right. So both of these are really important. And as you go on practicing, you'll be able to remember that in one of them, it is a decreasing one, and in one of them, it is an increasing one. Okay. Very similar to both of these, we have a transfer function which includes a time constant. It's of 1 upon ts plus 1 form, and the other one is ts plus 1 form. So you can see that this can be somehow analyzed to be similar to that of 1 upon s, right? So that way there is a corner frequency over here, and after that we have a decay of minus 20 dB per decade as soon as you get a pole. What is corner frequency? Corner frequency is omega is equal to 1 upon t. So this is also what we'll be looking into today. Okay. Next, what we had seen for ts plus 1, it is rising because we can say that it is comparable to s. All right. So all of these were things we had seen. Other thing was that, okay, for all of these whatever we discussed till now were first order transfer functions. What if we are given with second order transfer functions? So in all of those cases, our corner frequency is going to be the natural frequency of the system. Okay, you can see that when, because here all the comparisons that you're going to make is always related to omega n. So it is either below omega n or above omega n. In the earlier case, it was below 1 by t and above 1 by t. All right. So here also we can see that it is related to omega n. And yes, we did this. So this was a brief recap. Now, moving on to today's exercise. Okay. So we'll later see the Nyquist stability criteria. Let me adjust the window. Okay. No. Okay. So the first question is, consider a negative feedback closed loop system. Okay, closed loop system whose open loop transfer function is given to you. The slope in dB per octave. Okay, so I said earlier that we can have slopes in decibel per decade and decibel per octave. Both of these are valid forms. One of them just takes log 10, the other takes on the like log 2. Okay, so the slope of the high frequency asymptote in the magnitude plot of the corresponding sinusoidal transfer function is. So what you are essentially going to do, you are going to make a magnitude plot for this transfer function. All right. And do you see this transfer function is of the form what? It's a second order system. So it is going to be omega n square upon s square plus 2 zeta omega n plus omega n square. But in the numerator, we also have a term s plus 1. That means we have a 0 that would contribute in not falling of the decade, rather rising. We'll see that. Okay. So this is your question. Your open loop transfer function is given as s plus 1 s square plus 12s plus 20, right? We can factorize it, right? S plus 1 upon s plus 10 into s plus 2. By now, I hope you are very clear with what are the poles and zeros of the system. Uh, can anyone answer what are the poles of the system? Right. These are the poles of the system, minus 10 and minus 2. And 0 is minus 1. Okay. Now, what we are supposed, we want to find the slope in octave for high frequency region. Okay, so we'll move in a very basic way. So g of j omega, let's call this gs. Okay, then g of j omega is j omega plus 1 upon j omega plus 10 into j omega plus 2, right? We can write it in other form also, but this form also works, like time constant form. So I'll write it just for cleanliness. So it should be in this. All right. Now we want to find what is the high frequency asymptote. For high frequency asymptote, if we want to find high frequency asymptote, that means we want to first find the magnitude of this transfer function. So, uh, so uh, from the numerator part, when you try to find out the magnitude, it would be under root of omega square plus 1, right? When you write it to be omega square plus 1, since it is high frequency asymptotes, definitely this 1 will be neglected. When this 1 is neglected, you get under root of omega square. You can remove this and let it just be omega, right? In the denominator, you can have 20 into. Doing the same thing, you would just get omega on 10 here, right? And you'll get omega upon 2. So all of these cancel out and you get 1 upon omega. So this is the magnitude you are getting. And So this is magnitude of G of J omega at high omega is high frequency. Okay. Now we want to find out what is the magnitude, what is the slope. Okay. Slope of high frequency asymptote. What is it? Okay. So how do we define? So if we write this in decibel form, it would be 20 log of 1 upon omega, which is equivalent to minus 20 log 10 omega. You might see from here, this is a basic observation that everyone should make, that this quantity is Bode plot corresponding to 1 upon s, right? You get the same thing there. Now you have omega here. You can put minus 20 log 10 omega. Then you'll finally see that you have 20 dB per decade decay. I hope it is clear. I'll reiterate it. See, you got this when you try to find out at omega. Now, if we want to find out the same thing at 10 omega, this was already covered in the lecture. So, log 10, 1 upon 10 omega, right? Or we can directly write 10 omega, and here we can have a minus sign. Then, it would be minus 20 log 10, 10 minus 20 log omega, and base is 10. So, if you try to find out the difference between which quantities, this quantity and this quantity, what would you get? You'll just get this quantity remaining, and what it is? Minus 20. So when you move from omega to 10 omega, that means when you move a decade, either forward or backward, you can check it anyways. It was not necessary to have 10 omega. You could have checked for like 10 omega and 100 omega. It was your choice. But I chose omega and 10 omega just to see what is happening in a decade. And in a decade, what we can see that there is a decay of minus 20 dB. Okay. That's why we can say here that the slope of high frequency asymptote is minus 20 dB per decade. What is minus 20 dB per decade equal to? Minus 6 dB per octave, right? Did we have this in the option? Yes. The question asked was in dB per octave. Mind this, you might have this question in exam and do not try to answer for dB per decade. You have minus 20 as well in the option. Okay. All right. We'll move to the next question. So in the same problem, the corner frequencies of the sinusoidal functions are what? We want to know the corner frequencies. So corner frequency is given by 1 upon t, right? Okay. So what was, and okay, from here you can see we have 1, 10 and 2. 1, 10 and 2. So this should essentially be in the function of ts plus 1, or I would say t1s plus 1, t2s plus 2, and here it should be t3s plus, sorry, yeah, here it should be 10. So, or 1 only. Yeah. From here you can try to find out what is the value of t1, t2 and t3. Okay. So if you find, what you would get? T1 to be 1, right? T2 to be 1 upon 2. Is that correct? T3 would be 1 upon 10. So in one of the cases, you'll have 1 upon 10. Sorry, this would be 1 upon 10 and this would be 1. So the three corner frequencies in your case are 1, 1 upon 10 and 1 upon 2. So what is the relevant option we have here? 0.1, 0.5 and 1. All right. So these are the corner frequencies. So it is very easy to find out the corner frequencies. It's just that you have to see the transfer function. Check where all you are getting uh, time constant or in different factors. What are the frequencies that those terms contain? Figure out those frequencies. Write down there, and you have the answer. Okay. I hope this is clear. Okay. It's again related to the same question that the magnitude of the sinusoidal transfer function as frequency tends to 0. So we want to see as frequency tends to 0. In the first question, we saw that frequency was high frequency. So we neglected every term that came with it. In this case, we are just going to neglect the frequency itself. And we want to see what is the magnitude, all right? Okay, so please take a snap of this question because we are going to use it time and again for the 6 7 questions because that essentially gives you how it is going to be. So take a snap of this transfer function. It will help you throughout. Okay. Okay. So we want to find out the angle at low frequency. So g of j omega. Now it would definitely be angle of 1 plus j omega, right? It would be an angle of 20. So I am not given that form. Just let me. What was there? Plus j omega by 10, 1 plus j omega by 2. Okay. Now we want to find out angles corresponding to this. So in the first, so everything that is in the denominator has a negative phase. Everything in the numerator has a positive phase. 110 and 2. Yeah. I'm sorry. It would be 110 and 2. Because everything you have to, let me make it clear once more. So it was already in the format of T3s plus 1 and we wanted to bring this in this format. So here it would be like, yeah, it would be 1 upon T and T would be 1, 10 and 2. Sorry for the mistake. All the corner frequencies are inverse of the time constants that we have. Thank you for clarification. Okay. Okay, then we want to find out what is the phase here. So from here we can have 1 plus j omega by 10, an angle of 1 plus j omega by 2, right? If we try to find out the angles, what it would be? Can anyone tell me what is the angle for the first term? Like in the format of tan inverse only, nothing different. Right. So you take the imaginary part as the numerator and the real part as the denominator. So it's tan inverse omega minus definitely does not contribute to any phase since it is a constant. Then you have tan inverse omega by 10 and then you have tan inverse omega by 2. All right. We want to know what as frequency tends to 0, no? Okay, so just a second. There is another question for phase and there is a question for frequency. We are solving the phase part first and then we'll see the frequency, the magnitude part. All right. So let's see here. For low frequency, what is the angle that you are going to get? So it is tan inverse 0 minus tan inverse. It's going to be low frequency. This question is based on high frequency thing. If it were low frequency, it would have been all 0, right? Now, this says omega is low frequency. What if omega is high frequency? What would be the answer? If omega is high frequency, you'll get tan inverse infinity minus 0 minus tan inverse infinity minus tan inverse infinity. It would be pi by 2 minus 0 minus pi by 2 minus pi by 2, right? Cancelling these both terms, you'll get minus pi by 2. So the angle as the frequency tends to infinity is minus pi by 2. Make sense? Now we'll see for the magnitude, and for magnitude we are going to see as the frequency tends to 0. All right. So as frequency tends to 0, what would be the magnitude? We saw that earlier, right? Okay, I'll show. For finding the phase, just let me see. While finding phase, do we have to always make sure that GSN is in the form of this and this? Not really. You can have in another value also. Let's say, okay, I'll show you with an example. Let's say you have something in this form: s plus 1, s plus 3, s plus 4, s plus 5. If we have in this form, what you'll do? You will uh, like what we really do, what is the most important thing is that you convert it into j omega form always. Okay, j omega plus 3, j omega plus 4, j omega plus 5. Okay, once you convert it, multiply the denominator by the conjugate. So you'll multiply it by j omega plus 1 upon, I'll write it, j omega plus 3 into j omega minus 3, right? So you'll get rid of the any imaginary part in the denominator. Then you write j omega plus 4 into j omega minus 4, j omega plus 5 into j omega minus 5. Since you are multiplying with all these terms in the denominator, do multiply in the numerator as well. All right. J omega minus 3, j omega minus 4, j omega minus 5. Now, this part, this complete part is real, right? Because you multiplied with the conjugate, so you're never going to have any j term. Whereas in the numerator, it would be real plus imaginary. Then find tan inverse of imaginary upon real. This term would be common in both of them and will get cancelled out, and you will have this. Another case is if you have something of this form: s plus 1, s square plus 4s plus 5. Let's say of this term. Okay. Simplify this. You write here j omega plus 1, j omega square plus 4j omega plus 5. J omega plus 1 divided by, what is the j square omega square is minus omega square, right? Plus 4j omega, or I'll write plus 5 first because it is being included in the real part, plus 4j omega. Now multiply the conjugate of the denominator term here and in the numerator. You will get rid of any imaginary part in the denominator, whereas you'll have the imaginary part in the numerator, and you can again find tan inverse of imaginary upon real. So whatever you get, don't restrict it to ts plus 1 and 1 upon ts plus 1. Convert it into j omega format. Remove the things from the denominator by multiplying with the conjugates and find what is the angle that you are getting from the numerator in terms of tan inverse imaginary upon real. That's it. You'll always get the angle. I hope this makes sense. Or any other further doubt? Okay. Okay. Now, magnitude of the same transfer function as frequency tends to 0. Frequency tends to 0. What would you get? Uh, from here. Okay. I'm sure you have copied the transfer functions, so I don't need to go every time. So what you'll get? Uh, 20 log omega, right? Corresponding to this part in the numerator. Minus, not minus, just a second. 20 log omega, yeah. Then it would be 20 log 20 because it is coming from which part? From this part. Then we'll take corresponding to this part. Why we are using the minus sign so easily? Here everything is in numerator and denominator form, and everything is in the form of multiplication and division. But here, how are we taking it into plus and minus? Does anyone have an answer to this? Okay. So here, when this transfer function is given to you, this transfer function, everything here in the rightmost part is in numerator and denominator form, and all of them are in multiplication or division form, in multiplication and division form. But how are we writing them here in this form, like in plus and minus form? Right, right. So this should be very clear. This is very basic, that logarithmic properties help us in doing this. So the reason, one of the reasons why we go into logarithmic scale is we reduce the problems that we have with multiplication and division, and we simply go to addition and subtraction format. We make the things very algebraic, easy to interpret, something that can help us in using the superposition property. So that is why this log is helpful. Okay. Minus 20 log 20 minus, related to this part, we'll have uh, 20 log omega on 10 minus 20 log omega on 2, right? As omega tends to 0, we want to find out what is going to happen. As omega tends to 0, We saw something in the first question. Do you remember? As omega, so yeah, where did we see that? We solved this question. Yeah. So this term we did not see the same thing. I'll show you. So what it would eventually become? Can anyone tell me? As omega tends to 0, what we are going to see? We just want to see this for low frequency. We don't want to see it for high frequency. Now that should give you some hint. Minus 46. Minus 46 is not in the option. I think you have taken some, I don't know, you should have some other answer. Check once more the calculation. Try to come to this point that you get g of j omega as omega is equal to 0 to be equal to 1 by 20. Just the magnitude. See if you get this. Forget this thing. Then we'll convert it into dB format. And when we write it in that format, it would be minus 20 log of 20, which is minus 26 dB. But how do you get minus 1 upon 20? You should get from here. Okay. Try to figure this out by the end of the lecture, else we'll return here. Yeah. Yes, we can write this. So that's the same thing, no? That I had written. Tan inverse omega, tan inverse omega on 10, tan inverse omega upon 2 for the angle part. Yes. And one more thing is, if you write tan inverse of, so another real term that was there was 20. So it is tan inverse 0 upon 20. So you get 0 only there. So this is correct. For the last phase question, we can write this. This is correct. Okay. So in the same question, try to find the answer to this question, given that at low frequency, we already saw this now, g of j omega is equal to 1 by 20, right? We saw this. So what is the slope of low frequency asymptote? Can anyone tell? What is the slope of low frequency asymptote? You can pay attention to this detail that this at low frequency the magnitude is a constant. So given the magnitude is a constant, right, right. The slope is 0. Good. Okay. In the same problem, what is static position error constant? I would be very happy if you could revisit the formula. Otherwise, you should always remember that the static position error constant Kp is limit s tends to 0 gs hs, right? So as frequency tends to 0, what do you get here? It is the same quantity 1 upon 20 that we saw in the last question or last to last question. So it is 0.05. Okay, so steady state error. What is steady state error? I want to know this from you all. Steady state error is equal to limit s into something upon something we say. What is it? So when we had ys gs, no, ys upon us is equal to gs upon 1 plus gs hs. From here we had made some derivation to arrive at some sort of how it is related to the response. So can anyone tell me? We wanted to get yes and we did something. If you don't remember, please revisit the notes. But it is rs upon 1 plus gs hs. This was the steady state error formula. So it is limit s tends to 0. It is for unit step reference, right? Limit s tends to 0, s into rs is 1 upon s because it is step input, 1 plus gshs, and so this part you'll have s plus 1, s plus 10, s plus 2. Then you can write it to be equal to limit s tends to 0, 1 upon 1 plus 1 upon 20. So it is basically 20 upon 21, right? It would really be equal to 0.95. What in the problem? Here they are just KP. This question. Yes. I did not understand your problem. In KP, they have just asked, here they have just asked KP, but in problem, they mention low frequency. Oh, okay. So, when KPE is taken, it is taken at S is equal to 0, S tends to 0. Because, so, how do you define the static position error constant? Okay, steady state error. Okay, let me clarify this. Yeah, we can substitute 1 by 20. I'll tell you why. In time domain, when we want to find out what is the steady state error, it is limit t tends to infinity et, right? Using the final value theorem, it is limit s tends to 0 es, right? Sorry, ses. This is the way, this is what the final limit value theorem says. So here for finding out the KPE, we always want to have S tends to 0. S tends to 0 means omega tends to 0. Omega tends to 0 means this is low frequency. In questions is they asked us to see problem 1 where it is no problem problem 1 is only for reference to the transfer function. It is not for reference to the frequency. Okay, it is just for the transfer function and nothing. And for position error, it always has to be steady state error is found when s tends to 0, never at when s tends to infinity, never when omega tends to infinity. It is always at s tends to 0 and t tends to infinity. All right, so this is the case. So in all the questions, wherever they are referring, no, it is just for the transfer function and nowhere it is for any frequency. Okay. So from here it is, I hope it is clear that it is 0.95 here. It is just a simple steady state error value. Okay. Yeah, in the last class we did not do any MATLAB question on Bode plot, but for this same example, which we did till now, which we were solving for like 7 questions. So the way to I think if you all were present in my classes before this, I have shown the MATLAB code for root locus, but here I'm not changing the interface due to recording issues. So I have taken down the code here itself. So how do you define the transfer function? I'll clarify it once. So you can always use this as a tool to find that whatever plots you're making, are they correct or not? Here you do not have to go through all the steps. It is just a function which can be called. Okay. So what we wanted to do? We wanted to do for s plus 1 upon s square plus 12s plus 20. You can see it is written here. So s ka coefficient is 1. S to the power 0 coefficient is 1. So this is the numerator. For denominator, s square's coefficient is 1. S coefficient is 12. S to the power 0 coefficient is 20. Alright. This is your numerator and denominator. How do we define the transfer function? It is TF of numerator comma denominator. So this system is basically your transfer function. You can open MATLAB, not now necessarily, but you can write this code. This PPT would be made available to you definitely on the spreadsheet that is also shared with you. So you can write this code over there in the editor and then you can see what are the results. Then Bode of this system would give you the Bode plot. The grid is on, the title is written in this way. The output that you get is of this kind. Okay. So we saw now that at high frequency the phase would be minus 90 degree. You can verify this from here. Does it decay at minus 20 dB per decade at high frequency? It does. See, here it is 10 to the power 2. Here it is 10 to the power 3. The decay is minus 20 dB in this one decade. So you can verify all the questions that we did from here. All right. Now, Uh, so every question that was solved in the last class or anything that you want to see for Bode plot, you can plot it in this way, just changing the transfer function. It's that easy. Now, the plot of the real part of the sinusoidal transfer function and its imaginary part. Just a second. Hmm. The plot of the real part of the sinusoidal transfer function and its imaginary part as frequency is valid. I told you we have a plot of imaginary of p of j omega and real of p of j omega. And we'll see that it is called Nyquist plot. We'll have many questions now related to this. And this is pj omega plane. It's not S plane anymore. It is PS plane. Okay. Let's, before moving on to the questions directly, let's see this. Nyquist plot is a plot of g omega in the complex plane, which is plot of real part of the transfer function versus imaginary part of the transfer function as omega is varied from 0 to infinity. So this is what is the Nyquist plot. Okay. Now GS is equal to 1 by S. Uh, can you just give me a heads up if you have already gone through the lectures? Then I would be getting fast with this. Okay. Okay. Arya, I think for you also it is clear. Then I'll move forward. So if it is 1 upon S, then what actually happens is, or what we actually do here is, we vary the omega from 0 to infinity. It can be 0, 1 by t and infinity. We find out the real part of the transfer function, the imaginary part of the transfer function, the magnitude and the angle. Okay. We find all of them and then we try to plot over here. In some cases, you find that it is going to be a circle. So it is generally of this nature, and we'll see in the questions also that we'll be dealing with now that yeah, it can turn out to be a circle, and if it is a circle, we can find out the radius and so on by taking 2 points essentially. Omega is equal to 0 and omega is equal to infinity. Oh, how this circle equation came? So it is mainly an intuitive way. So what happened when this as omega was varied from 0 to infinity, all the values were taken on the plot. So for, you can see, for omega is equal to 0, we got this value where imaginary part is 0, real part is 1. I'm sorry, this is for omega is equal to infinity. Yeah. For omega is equal to infinity, we got 0, comma 0. For omega is equal to 0, we got 1. And what we can say is that when you generally have the plots of this type, this nature, it is generally a circle, because in Nyquist plot you always have the mirror image when omega is varied in the other direction. Okay, so it is generally a mirror image, and for mirror image you get a circle. So before that you can say that okay, this is a semicircle. Moreover, if you try to get more points, so you took for omega is equal to 0, took for omega is equal to infinity, take for some more points, and then you see that it is a circle. Now, after finding out this is a circle, this is okay. I'll explain it. This part, this 1 upon 1 plus t square omega square is the real part here. This part, imaginary part, is the one here. When you see, by finding out all the points, it is a semicircle, then you can determine that okay, there should be some center, right? So it is from all the points only that you understand that it is a circle. Now, if once you get that it is a semicircle, you know that What is the equation? This is the general equation of a circle. If you find out that it is already a semicircle, then it should have a center along its diameter. Then you come to know that okay, 1 by 2 is my center point. At what distance it is from the circumference? It is at a distance of 1.2 only. Hence my radius is going to be 1.2 only. So this is done. Then all the points are at a distance from the imaginary and real point. So your x is the basically real coordinate, y is your imaginary coordinate, and when you subtract minus 1 by 2, that means what is the center of the circle? For imaginary point, the center is 0. So here it is by default 0. You get 1 by 2 square. So this is the way in which we try to find out what is the equation of this circle. I hope it is clear. So if you in general want to find out, okay, if this is a semicircle or not, then you have to plot multiple points and you have to see that all the points just have the distance to be equal to that from the center. So the first thing is intuition, then you build upon it. B is equal to Z. Okay, so A and B are center of the circle, right? In our case, what is the center? It is this point. This is your center, right? Which is 1 by 2 comma 0. Right? The real part is 1 by 2. There is no imaginary part. That is why this came here. 0 came here, 1 by 2 went here. Okay. Okay. We had other questions in which there was some time constant and then you tried to find out what is the Nyquist plot in this case. So all of these were already covered. We'll proceed with the questions. Okay. So, which one of the following statements is true about Nyquist plot of s plus 2? If you want to find out the Nyquist plot of s plus 2, what we'll do is, okay, let's see this question. J omega plus 2. Okay. Now, your real part of the transfer function. What it is? 2. Imaginary part of the transfer function is what? It is omega. When you draw the Nyquist plot, what do? You vary omega from 0 to infinity, right? You vary omega in this way. This real part is always going to be 2. Oh, I did not give a MATLAB plot for this, I think. Okay, no problem. But see what you're going to do. This real part is always 2. How did I miss it? Just a second. So it would be a constant line actually. I forgot to put the plot here. But you can also draw it on your own and it is very easy. So, okay. So your real part is always 2 and as omega is varied from 0 to infinity, this would always be positive. So my real part is positive. My imaginary part is also positive forever as the omega is varied from 0 to infinity. So it is just going to be this line. Just this line. This would be omega is equal to 0. And this would be omega is equal to infinity. So you are going to have this line only. This is your real part. This is your imaginary part. Make sense? Yeah. Straight line from x is equal to 2. Vertical. Now, when you give the same command to the MATLAB, what it would do? It would plot another line in this direction also, because the Nyquist plots are mirror image about the real axis. So you'll get in the MATLAB plot, you'll get here also. But what you're supposed to remember that it should go from 0 to infinity only. So it is going to be just this line. Alright, so it is always going to be in the first quadrant only. So we have the answer here. So we do not really need to plot the complete thing, that what is the angle, what is the magnitude. You get a sense from here itself. Okay. Now we move to the next question, that we want to find the Nyquist plot again here, and the question, it is written that it is going to be a semicircle. If it is given that it is a semicircle, it has to be a semicircle. Do not try to find out if it is a semicircle or not. Try to find out what could be the intersection points, and then we'll see that what is the center. We'll see this. Just wait. So g of j omega is 1 upon j omega plus 4. All right. Now, just a second. Okay. So what we want to plot the Nyquist plot, and we want to find out what is the semicircle radius. Fine. What we can do as a very first step is, we can try to find out where is the like what is the magnitude, separate it in real and imaginary part, and then try to find out what is the Nyquist plot. All right. So basically what we have to see is what is happening at omega is equal to 0, what is happening as at omega equal to infinity. So let's start doing. Uh, let's multiply it by the conjugate to solve any sort of problem in the denominator, and how we can separate it into imaginary and real part. So you see, from here you cannot get real plus imaginary. We want real plus imaginary. So because of that, we need to have it being multiplied in numerator and denominator. This is 4 plus j omega. This is 4 minus j omega. This is also 4 minus j omega. All right. So it is 4 minus j omega upon 4 square plus omega square. It's clear? Now we can separate it. 4 upon 16 plus omega square minus j omega upon 16 plus omega square. So this is your real part. This is your imaginary part. Okay. Then we want to analyze the Nyquist plot. Since it is already given that it is a semicircle, it would have somewhat this nature only. Okay. And it would basically cut at omega is equal to 0 and omega is equal to infinity. So this comes with practice. Else you can do everything to check what is happening. You can make the same table that is made in the lecture to figure out what is happening. But I would check for omega is equal to 0 and omega is equal to infinity, what are the real and imaginary parts. If I get both of them to be on the real axis itself, I would know that, okay, the real axis is going to serve as a diameter, and hence we can find out the center somewhere here only. So let's see. So, okay, this is your real part and this is your imaginary part. Now, we'll see what happens at omega is equal to 0. You can plot the complete table, but I'll show J0. I'm trying to find out the real part first. What is, okay, I'll make a table only. This is real. This is imaginary. This is omega is equal to 0. And this is omega is equal to infinity. Yeah, you already know the answer. That's good. But still, then I'll proceed in shortcut now. So it is, uh, okay, 4 upon 16, right? And here the imaginary part would be 0. Then the real part here would be 0, and imaginary part would also be 0. Hence we can say that it is 0.25 and here it is 0, the real parts. That means this part would be, uh, it would start from like from here. It would have this to be 0 over here, and this part would be 0.25 comma 0, and hence this whole thing is 0.25 only. Then my radius will be 0.25 upon 2, which is 25 upon 200, 1 upon 8, 0.125. Very good. Okay, now this is the same question that we have done. You see the difference here only is this Nyquist of the system. You can copy this whole code and run in MATLAB, you'll get the plot. The plot would look like this. So whatever you did now is justified here. By finding values for omega is equal to 0 and omega in it, we can get diameter. From that we can divide by yeah, but like you have to be sure that it is going to be a circle or semicircle. Then most probably you'll get the answer every time. Like when you make the same table that is given in your lecture, you find for omega is equal to 0, omega is equal to infinity. If you get both the points on the real axis, see here in our case what happened? One point was 0 comma 0, one point was 0 comma 0.25 comma 0. These were the points. So I knew that it is here only on the real axis. So when I knew it is on the real axis, I could find that, okay, this is going to be my diameter. But let's say, if these were not my points for omega is equal to 0 and omega is equal to infinity. Let's say my points were, um, okay, this was 0 comma point 0.1, let's say. Then it would be x is equal to 0, y is equal to 0.1, somewhere here, and this point would be somewhere here. So the Nyquist plot might go some other way, like this or some other way. Then we can't say that this is going to be the diameter of the circle. Okay. So for that, for applying this method, or not this method, this trick, you need to be sure that both of these points are on the on the real axis, or they are on the imaginary axis. Somewhere they have to be in a symmetrical situation so that you can know that, okay, the line which is falling inside my circle area on the real axis can serve as the diameter. Otherwise it would just be a chord and it would not be a diameter of the circle. You won't be able to find the radius. So doing this is important, and interpreting both these values important. Then you'll be able to find out. I hope this makes sense. Okay. Make the habit of preparing the whole table and then figuring out what is happening later. Okay, so this Nyquist of the system, this is the circle plot that we've got. Okay, now the Nyquist plot of this system. So in the notes, I haven't taken right now, but you might have seen that there is some Nyquist plot related to the time delay system. So it is the similar kind of question. Okay, so we want to plot this. G of s is e to the power minus 2s. Okay, so g of j omega is equal to what it is, cos of 2 omega minus j sine of 2 omega, right? I hope this makes sense. And after this So if you try to find the magnitude, since it is cos and sine, again it is coming from some intuition. So what it is? Magnitude is under root of cos 2 omega square plus sine 2 omega square. This is your magnitude, right? And if you remember, cos square 2 omega plus sine square 2 omega is always 1. That means it is going to be a circle of radius 1. Okay? So since it is cos and sine term only, and we know that its squares are equal to 1, it gives you an equation of circle with a frequency of omega. Now, if we were supposed to draw the Nyquist plot corresponding to this question, how would we draw in MATLAB? Like e to the power minus 2s cannot be defined as some numerator and some denominator. You cannot express it as some numerator in which the coefficient of s square is this. Yeah. Yeah, it is correct. So basically, or you can also use this Paid's approximation that was taught to you. You can use first order, second order is more appropriate. So what MATLAB really does is you can express this exponential time delay as a ratio of this polynomial, right? It is doing the same thing that you have done. It is just that it has been broken in two parts, e to the power minus s minus e to the power minus s. In the numerator also you are having one term. So it is e to the power minus s upon e to the power s. And this has been written in this way. Okay. So both of these ways are correct. The Paid's approximation is already inbuilt in MATLAB. Okay. So you just define the time delay, which in our case is 2. You write what is paid numerator, what is paid denominator, which is given by paid time delay, comma 1. So it directly figures out if you have given paid, if you called paid function, you have given the time delay, then, and there is nothing in the denominator, so it is 1 by default. You call it paid numerator and paid denominator are taken directly in the form of transfer function in this form. You don't need to write this. Okay, it directly takes it in this form using paid function. And then you define system paid is transfer function of paid numerator, paid denominator. Then you can plot the Nyquist plot. And this is the circle. Circle with a radius 1. It is no 0, 1, 0 and 1. Radius is 1. Alright. These MATLAB functions are really handy, will really help you to check all your results. Do refer to them. Okay. So, moving to the next question. Which one of the following is true about this transfer function or this factor basically as frequency is varied from 0 to infinity? So, let's write this what it is. G of j omega is, let's substitute j omega minus omega square plus 4j omega plus 2. Then you can write it as 2 minus omega square plus 4 omega times j. Now, this is your real part. This is your imaginary part. Without plotting it completely, we'll try to find out what is going to happen in which quadrant it is going to lie. Alright? So, as omega is varied from 0 to infinity, what happens? How would real part behave? At, let's say it was 0 initially and it goes till infinity. So the real part would have positive and negative sign both, right? because it starts from 0 and goes till infinity. Whereas for imaginary part, it is always going to be positive. So if you draw this real and this is imaginary, you are going to get this part. So it would always lie in the first and second quadrant of the complex plane. When you, okay, no plot for this. Okay, again, this is a similar question. Yeah, the similar question in which you had doubt. So if it is going to be a semicircle, it is already given in the question here. So you're supposed to find out the radius. Now we'll see again that for omega is equal to 0, do we get something on the real axis? For omega is equal to infinity, do we get something on the real axis? If it is so, then we'll try to find out what is the center and hence what is the radius of the circle. So let's see this question. Okay. So let's multiply with the conjugate. Mm, you should get this. Do check. I'll take this J out. This is your real part and this is your imaginary part. Now what we'll do, we'll check for omega is equal to 0 and omega is equal to infinity. The real part and the imaginary part. For omega is equal to 0, it's going to be 1 by 5. That means it is 0.2. The imaginary part is going to be 0, right? For omega is equal to infinity, what you're going to get? What will you get for omega is equal to infinity? How will you find out? We cannot proceed directly. 1 and 0. Ah, yeah, right. So how do we get 1? Just for the sake of explanation, 20 plus omega square, divide both sides by omega square. Yeah, very good. 100 upon omega square plus omega square upon omega square. This becomes 1, this becomes 1, this becomes 0, this becomes 0. So you get 1 here. Okay. And for imaginary part, it is going to be 0. So you see again, you have both of these on the real axis only. So it is 0.2 and it is 1 and you're going to have a semicircle in between. Now we just want to find out that what is the radius. Radius would be 1 minus 0.2 upon 2. That means 0.4. Okay. So your radius is 0.4. Okay. Now, so this is again the plot for the same thing. It is plotted in a very same way. And you can observe from here everything that we have done. The radius and all. Now, in the last question only, what is the phase? So, yeah. So, again, the question that you asked in the beginning can be justified from here. I'll copy this. So this was your transfer function, right? Now we want to find out what is the phase. So because in this question I multiplied by the conjugates, I just have real part in the denominator, whereas real and imaginary part in the numerator. So just finding out what is uh, denominator upon numerator would give you the answer, tan inverse of this thing. Okay, so what is the maximum phase of the sinusoidal transfer function? It is right. Okay, it is the maximum phase. Okay, whatever maximum phase it is going to be. Let's say what is the angle going to be at first. Let's see that. So your angle of g omega is tan inverse of 8 omega upon 20 plus omega squared. I'm sure this is clear. Now let's see what is going to happen. So we already know that it is a circle, right? So let's plot it to be a circle. It was at 1 and 0.2. Yeah, here it is 1, here it is 0.2. Imaginary, this is your real. Let's say we have a circle over here. You can check that it would be going from this direction by taking one more intermediate point. Okay. Oh, sorry. I'm not going this direction. In the MATLAB, it gives you both the plots, but here it would be this one. Now, what we actually want to find out, the maximum phase of the sinusoidal transfer function. Phase means tan inverse of imaginary upon real is maximum. Then let's say it is maximum at some point. This phase is maximum at some point. Okay, let's assume that it is maximum at that point. What was your center? It was 0.4. Okay, at whatever point it is going to be the maximum, it is definitely going to be a tangent, right, to the circle. Because if if it were not a tangent, what would have happened? If it is in this line, there is no maximum phase because this part is not lying on the Nyquist plot. If it is in this line, it is definitely not a maximum because this and this point are not maximum. So whenever it is going to have a maximum phase, that means it should be acting as the tangent of the circle, right? Now, when this is a tangent to the circle, this is 90 degree because it is a tangent. Then it is perpendicular to the line joining the periphery of the circle to the center. So you can find out that sine of this phi m is zero point 0.4, this thing, divided by the hyper, sorry, have I done some mistake? Have I written the center of the circle correctly? No, I haven't. Zero point 0.4 is not the center, zero point 0.6 is the center of the circle. The radius was 0 0.4, right? Sine phi m to be equal to 0.6 upon 0.2. No, it should not be that. So sine phi m, this is your sine phi m, means the perpendicular line, this one, which is the radius. What is your radius? It is 0 0.4, right? 0.4 upon the hypotenuse. It is 0.6, right? Sine phi m would give you any value between 0 and 1, no? 0.6 upon zero point 0.2 would give you 3. So it is going to be the radius upon the distance to the center of the circle. So it is 2 upon 3. Find out sine inverse 2 upon 3. You'll get the answer. What is it? Yes, it's 41.8 degrees. Okay, just one more question. That is a very easy question. As frequency is varied from 0 to infinity, the Nyquist plot would always lie in which quadrant? So we already saw the, okay, I'll write it. G omega is 20 plus omega square plus 100 plus omega square plus J8 omega upon 100 plus omega square. Real, imaginary, uh, what do we say? Omega is equal to 0, omega is equal to infinity. As omega is equal to 0, you get 0.2. Omega is equal to infinity, you will get 0. Here you get 0 and here you get 1. Okay. So we already saw the same question that it is always going to lie in the first quadrant. You can plot one more intermediate point just to make sure that it is in the first quadrant and not in the fourth quadrant. Okay. So always try to plot at least one more point so that you get the quadrant in which it is. So it is in the first quadrant. Like for this, you can always try to plot at the corner frequency. When you plot at the corner frequency, you'll get that what is the value, positive or negative. Just saying positive or negative for the imaginary part would also give you a hint if it is in first quadrant or fourth quadrant. Yeah, it is first quadrant. So you got first quadrant here. When I think, okay, I do not have MATLAB plot for this, but you can just write this transfer function itself in your MATLAB and you will be able to see a circle. But you will see the circle in first and fourth quadrant both because it is basically a mirror image or symmetrical about the real axis. So you'll be able to see both of them. Alright. So we are done with the today's lecture. In the next lecture, what we are going to see is Nyquist stability criterion. And I think we have just 2 more weeks left, and maybe then we'll have an extra session. The extra session is for you, so I'll be taking the session, one extra session also, and the extra session is for you to go through all the problems again, sort of revision class. In case you want to do MATLAB problems, you can do that also. So all of them are applicable for that day. But before that, the next time we are going to see Nyquist stability criterion, in which we'll be able to find out how do we determine the stability for the system using the Nyquist plot. Then the last lecture would be based on lead and lag compensators. That is also one of the methods. We design essentially the compensators for our desired performance specifications and all of that. So we'll see both of these lectures later. Okay. Okay then. Yeah. Thank you. I'm stopping the recording.